are now recording. Let's get the screen set up from current slide. Okay. Okay. Now we did, let me just glance here for a minute. I didn't go far enough down. Okay. This is where we're starting today. Hold on. Turn on the projector. All right. Here's the other announcements I wanted to make. And sorry, it seems like every week there's something that sort of messes up my office hours. This is especially bad, so not super bad, but a little. All right, number one, Fridays normally I'm on the Birmingham campus, 7:45, 11:45. Not this Friday. I wasn't there last Friday. I won't be this Friday. And guess what? I won't be next Friday either because that's a holiday. Veterans Day is next Friday. Okay, but this Friday I won't be there because I have another treatment. Now, my treatment last Friday went well. I was there at 7:30 or before, did blood work and stuff, started the treatment, and about midway through it, I started breaking out itching and rash, so they gave me another Benadryl. It cleared it up, and it was fine, but they slowed down the drip because of the rash, and it took pretty close to the 7 hours they said it would, and that was for 300 milligrams of medicine. Okay. Now, this Friday, I've got 1,000 milligrams. This is a normal dose. That was the introductory dose, the first time, just to see how it worked. And they said that usually if you have a reaction, it's going to be the first time. After that, sometimes you don't. So I'm hoping this Friday, because last time they had to slow it down because of the rash, but it cleared up, but they stopped it until it cleared up, and then they started back at slower speed. Hopefully this time we'll get through, but it's still probably going to take 7 hours. Okay. I have to be there at 6:30 this time for blood work. 7:30 they're going to start, and then we'll go from there. So I will not be on campus Friday at all. No way. I'll be over there almost the whole day. In fact, probably the whole day. All right. Then here's another thing that's coming up. Next Tuesday, I have a doctor's appointment. My hematologist only sees patients on Tuesday mornings. So I'm going to miss at least 2 classes. So I've already talked with the first class, and they have said they wanted to make up the class because I like to make up classes if it's my fault. If it's the school's fault, I don't mess with it. But if it's my fault, I like to make them up. And they said tomorrow afternoon at 12:30. So normally I have office hours on Tuesday and Thursday from 12:15 to 3:15. Tomorrow it'll be 1:45 till 3:15 because I'm going to make up that class set. Then next Tuesday when I have the appointment, I'm guessing that I'll make up my differential equation class then Tuesday, probably 12:15. Maybe 12:15 or 12:30. 1:45 then. So both of this coming tomorrow and next Tuesday, my office hours are shortened because making up classes. My 11 o'clock class, I think I'll still make on that Tuesday, so I don't think I'll have to make that one up. All right. After that, I hope, there is one more. Next Thursday, 1 week from tomorrow, we have a faculty meeting at 2:30. So my office hours are normally 12:15 to 3:15. But next Thursday, hopefully I'll be through making up classes, but I'll have to leave to go to the faculty meeting probably about 2:15. So my office hours are only going to be 12:15 to 2:15. And then I'll be in faculty meeting. Then I hope I'm going to leave faculty meeting early so I can make my 3:15 class. So, this Thursday, Tuesday, and Thursday, shortened office hours. This Friday, no office hours. Next Friday, no school. Okay, so, all right. Those are the announcements I know about. Do you have any questions before we get started? All right, we were on page 402, chapter 7, section 7.5, and we did part A of example 5, but we didn't have time for part B. Okay? So, let's do part B. Part B is to do this integral. The integral of 18, looks a lot like the last one, doesn't it? Over x plus 3, still looks a lot like the last one, times x squared minus 9. There's the difference, okay? Dx. Okay. Last time that was x squared plus 9, which meant that was a non-reducible quadratic. So we had to deal with that, and that gave us an inverse tangent in our answer. Okay? This one, however, what can we do? What's that? Okay, no, you don't want to, because you see this will now factor. The other one with a plus there was non-reducible. This one can't be reduced. So we're going to factor the x squared minus 9 into
x minus 3
times
x plus 3.
Exactly. Okay? So you already have one x plus 3. You're going to have another x plus 3. So you're going to have a repeated root at x equal negative 3. And you're going to have one at x equal 3. So what they did is take that, and I'm going to expand it now for you to see, but then when I write on it, I'm going to have to shrink it back again. But that integrand becomes this. 18 over x plus 3 times x squared minus 9. We factor the x squared minus 9. That gives you x plus 3 times x plus 3 is x plus 3 squared times x minus 3. Now, with that one, we do, which they haven't shown this, how would you proceed from there?
We can put x minus 3, a over x minus 3.
Okay, a over x minus 3 or x plus 3, it doesn't matter. They do it over x minus 3, you're right. And then they do a okay, to the first power, but then a c over x plus 3 to the second power. Okay? So where would you go from there? So that's how we do. So you notice we don't have an irreducible quadratic, but we do have a quadratic in a repeated root. And you just put the c. So what would we do next? Multiply by least common denominator. Of course, it's going to shrink when I do this. And what is that least common denominator? X plus 3 times x plus 3 squared times x minus 3. This multiplies x plus 3 squared times x minus 3. This multiplies by x plus 3 squared times x minus 3. And this multiplies by x plus 3 squared times x minus 3. Okay. In the first, on the left-hand side, everything in the denominator disappears. Okay? So you're just left with 18 on the left-hand side. The first term on the right-hand side, the x minus 3 goes out. Right? And that leaves us a times x plus 3 squared. On the second one of the x plus 3 goes out, leaving another one, so that'll give you a plus b times x minus 3 times x plus 3. You see, you still have one of those left. And on the third term, the x plus 3 squared goes out, so all of it goes out, and that leaves you with a plus c times x minus 3. What's your next step? Okay, how do you mean?
Can we divide both sides by x minus 3 and x?
Okay, that'll get you back to a thing that you just undid. Okay,
Can you just take the square and the parentheses off?
oh, you mean multiply them out?
Yeah.
Okay, you could, but let's not. Okay, and here's why. Remember, this is the step that we choose some x's to simplify. Remember? We'll do,
Oh, like
yes,
yeah.
let x equal, which one do you want to do first? Yeah, let x equal
Minus 3.
-3, okay? Now, what would the left-hand side become? 18, that stays 18. And on the first term, it goes to 0. Second term, it goes to 0. So you're left with just a c times -6. So what does that produce c to be? Second? -3. Perfect. Okay? What do you want to do next? +3. Okay, what will the left-hand side be? 18. That doesn't change. Second? Yeah, I couldn't hear it. 36, exactly. Okay, I was listening to see if that might be Marcus coming in, and it was. Okay? We're doing the B part of example 5 on page 402, chapter 7, section 7.5. We did the A part last time. We're doing this. So we're down to the point of letting x equal +3, and that would be 36a and the rest of it gone. So what does that produce for A? One over 2, is that what you said? 1/2. Perfect. Okay, nothing else we can substitute. We still need to find the B. So what we do is plug in A and C and solve for B. So the left-hand side stays 18 is equal to, now A was 1/2, so this will be, and now you do have to multiply, that'd be 1/2 times, and let's square the x plus 3, what would that give you? Square x plus 3. X squared plus 6x plus 9 plus, now we can't do anything with the b, so let's just write it down, but let's multiply those two, and we know what that multiplies to be, what? X squared minus 9 plus, and c is actually a -3, so let's change that. Plus, sorry, to a -3 times x minus 3. Okay, now I'll jump up above and continue this. That would be an 18 is equal to, and I'm going to multiply through, that would be x squared over 2 plus 3x plus 9/2 plus bx squared minus 9b minus 3x plus 9. Okay. Now, I think the easiest thing, and I may be wrong, but I think the easiest thing to solve for would be the constants. Notice here, plus 3x minus 3x, that adds to 0, so that doesn't give you anything. Actually, though, now I take that back. I think that maybe the easiest thing would be to solve for the x squared. So let's do 18, well, your x squared terms on the left. What are your x squared terms on the left? Are there any x squared terms on the left? No. So that would be a 0 on the left is equal to 1/2 x squared plus b x squared, okay, which is b plus 1/2 times, well, just b plus 1/2. We don't need the x squared. We're doing the x squared terms. It's just b plus 1/2, right? You're doing the coefficients of x squared. Coefficient of x squared over here is 0. Coefficient of x squared here is 1/2 plus b. Okay?
Since there is no anything in that.
So again?
Because there is no anything in that.
There's no x squared on the left, so on the right it's just, okay? And actually, let me take off those parentheses. They're not adding anything. And what do we have? B is equal to negative 1/2. Okay. So now we go, and I'm going to erase some of the other mess I did here just because it's hard to read. So I'm going to erase all this down here. We've used it, so we don't need it any longer. But what we want is to rewrite our integrand so that we have our new integral. So this will be the integral, and you see we rewrote the integrand here as that. A was 1/2, so I'm going to put the 1/2 out front, and that was dx over x minus 3. See from here? Okay. And the b was minus 1/2, so that's going to be minus 1/2 the integral of dx over x plus 3. That's from here, right? Okay. And then what was our c? Minus 3 times the integral of, there it is, I lost it there for a minute. I'm going to rewrite this as this. X plus 3 to the minus 2 times dx. Is that okay? It just makes it easier to integrate, I think. Okay? Now, now that we've got that done, I'm going to erase so I have more room to write. I don't think I'm going to need this anymore because I've already accomplished what I can with that. Okay. Okay. First integral will be 1/2 the natural log of x minus 3, absolute value, minus 1/2 natural log of x plus 3. I'll put that in absolute values too. Now, how about that next one? Minus 3 integrate that. No, if that were x squared plus 3, we would. But it's x minus 3 squared. Okay, if nothing else pops up, you might want to think of substitution. Okay, what might you want to substitute? X plus 3. Okay, then du is equal to dx. Yeah, 1 dx. Okay, or just dx, right? So this would then be minus 3 times the integral of u to the minus 2, right, du. Does that integrate? What's that? Yeah, it'll be a negative 1, so we're going to make that a plus 3, u to the minus 1, right? Yeah, and yeah, I already taken care of the sign. Now, if you don't believe that, take a derivative of it. Minus 1 times 3 would be a minus 3 u to the minus 2. Yeah, that's exactly what you got there. Okay, but the u is, so that would be x plus 3 to the minus 1. So you could write that as now a plus 3 times 3 over x plus 3. And then, of course, what else do you need? Plus c. You got it. All right. Now, we can simplify that a little bit. We can write this as natural log of x minus 3 to the 1/2 power. And to the 1/2 power is, okay, we'll just leave it there, minus natural log of x plus 3 to the 1/2 power. And then the rest stays the same, plus 3 over x plus 3 plus c. Okay? But then you can combine those natural logs to be natural log of x minus 3 over x plus 3 to the 1/2 power plus 3 over x plus 3 plus c. Sorry. There we go. Now, I bet you they'll take out the absolute value bars. I don't know for sure why you can, but I think you can. Let's see what they got. No, they left it. Sorry. They left it in the earlier form. Okay, 1/2 log absolute value x minus 3 minus 1/2 log absolute value x plus 3 plus 3. I put it over x plus 3. They wrote it times 3, x plus 3 to the minus 1. It doesn't matter. Plus c. That's it. Very good. So, I find that easier if you can factor that denominator than if you had a plus in here and then you have to have that inverse tangent term. They're both pretty easy, but I like a little bit better to do that. All right. Now, let's move on to example 6. Okay? And we're going to get there ultimately, but let's see how we start before we get there. Were there any questions on 5A or B? Okay. Example 6 is the integral 4 minus x over x times x squared plus 2 squared. Oh, wait. Yeah, squared. Dx. Okay. How would you begin this one? Okay? And what would that produce? Say again? I couldn't hear you. Okay, oh, okay. All right, so let me do this. 4 minus x over x times x squared plus 2 squared would be a over x, got it, plus, okay, not just b, bx plus c over x squared plus 2 plus dx plus e. Now, they probably do b1s, b2s, and c1. Yeah, I mean, whatever you name them, they're things over what? X squared plus 2 squared. Yes, that's how we proceed. Okay? Now what? And that least common denominator is x times x squared plus 2 squared. This is times x squared plus 2 squared. This is times x squared plus 2 squared. And this is times x squared plus 2 squared. Okay. Now, what happens on the left side? Everything from the denominator disappears. And you have just a 4 minus x. Good. Next. First term on the right. Yeah, the x's go out, and you have a times x squared plus 2 squared plus, and here one of the x squared plus 2's go out, so you're left with, I'm going to write this a little differently, x times, and then I'm going to multiply those two together. Is that okay? For those two, okay? That would be bx cubed, you buy that? Okay, plus cx squared, that would be the innards, okay? Wait, yeah. Plus 2bx, that would be the outers, and plus 2c, that would be the last. Okay? Plus, now on this one, the x squared plus 2 squared goes out. Thank you very much. And this leaves me with a dx squared plus ex. Right? Now, to keep from writing that line over again, what I'm going to do next is multiply through by the x's. Is that okay? So I'm going to take out this x and the parentheses and raise the power of each of those x's. Okay? And what that will do then, that would be bx to the fourth, wasn't it? Because it was cubed times x is fourth. Cx cubed, bx squared, and cx. Okay, that was a sleight of hand, but are you okay with it? Whoops, I also need to do something with the first one. Let's square the x squared plus 2. Is that okay? What would that be? Okay. Square the x squared plus 2.
Okay, it's going to be a squared plus 2.
Okay. That'll be a to the fourth plus 4a squared plus 4. Right? You like to forget that middle term, don't you? Okay, no. I didn't do that right. Wait. That's an X there, not an A. I don't know where that came from. I was looking at it saying, Where did that come from? Okay. That's x squared. Okay. And then when you multiply a by that, again, I'm going to do this at once rather than doing it many times. Okay. That will be ax to the fourth plus 4ax squared plus 4a. Do you buy that? Okay. Now. Okay. Now. Why did I? Oh, yeah. There's only one thing you can really do as a simplification, and that's let x equal. We should have really done it here. I forgot to. X equal 0. Because you see, this factor here, this x, you see, this one you can't put anything in to make it go to 0, but you can with that. So let x equal 0. That's going to be an easy one. What does the left-hand side become? So let x equal 0. So this will be a 4 is equal to, and notice here, the ax to the fourth is 0, 4ax squared is 0, but 4a is not, so that's going to be 4a plus, and then every one of those next 5, all of them are going to be zeros, right? Okay, so that gives you what? A is equal to 1. Okay, that was our easy one. Okay, the rest of them we're going to have to do a little more work. So, sorry. So let's start with the quadratic terms. Are there any quadratic terms on the left? No. So, okay, so that's going to be 0. And on the right, you got an A plus B. Okay. So 0 is equal to A plus B, but guess what? A is equal to 1, so this is equal to 1 plus B. And if 1 plus B is equal to 0, what does that imply? B is equal to negative 1. Very good. So that wasn't too bad. Sorry. Let's do the cubic terms next. What cubic term do you have on the left? Nothing. So that's going to be a 0 again. And cubic terms on the right. Okay. Don't see any in the first group. That's just going to be a cx cubed. Well, we don't need the x cubed. We're just looking for the coefficients. C. Okay. And then none others. So guess what? C is equal to 0. Ha! A is equal to 1, B is equal to negative 1, C is equal to 0. Let's go to the quadratic terms. Okay? What quadratic term do you have on the left? Nope, quadratic. 0. No x squareds. So that's going to be 0 equal to, now quadratic term here you have 4a. We're leaving off the x's. Over here you have a plus 2b plus d, right? All right, but we know what a is. That's plus 1. Okay, so that's just going to be a 4. And our b is minus 1, so that's just going to be a minus 2, right? Okay, so now we have 0 is equal to 2 plus d, so that implies that d is equal to, second, negative 2, isn't it? Negative 2. Okay? And we just got one left, and that's going to be our good old e. Okay? So, let's do the linear terms. Do you have a linear coefficient on the left? What is it? Negative 1. Okay? Okay, any linear terms here? Those are all even terms, so that doesn't. Here we have 1. This is equal to 2c, right, plus e. Those are your x terms, right? But what was c equal to? 0. Okay? Yeah. So guess what that leaves us with? E is equal to -1. Ha! I think we've got it. Now, if you wanted just to check the constant terms, you could do that too. I like to do it just to make sure I did it right. The constant terms on the left is 4. And the constant terms on the right would be a 4a, but a is 1, so that's going to be 4. Okay? And that's the only constant term. Yeah, 4 is equal to 4. So yeah, that works. So we got them all. Okay. Now with those in mind, let's, I'm going to erase some stuff that I don't need anymore. Like I don't need this line anymore. But, well, I sort of did, but I can live without it. That thing that was in that was your integrand was going to be this. I erased too much, but I think we're okay. This is what we started with. And I don't think we need this anymore. Sorry, this is taking far longer than I wanted it to. It's just so slow. Yesterday, my pen was so terribly slow in one class that you just had to write and then sit and wait for it to show up. It's a little better today. Now, what I lost is that square. Okay, that was equal to this. So, let's rewrite our integral then as a was 1. So that's the integral of dx over x, right? Plus, and we'll do the next integral. B was -1, so basically, and c was 0, so that's going to be a minus x over x squared plus 2, right, dx. And then your last part, the d was a -2, so I'm going to write that as I'm going to pull out the minus, okay, and the d is going to be 2x, and the e was a -1, so that's going to be +1, because I pulled out the minus from that, over x plus 2, no, x squared plus 2. I can't write, goodness gracious. Okay, x squared plus 2 squared dx. Do you agree that's what our integral becomes? Okay. So I think I can get rid of my other thing here. So let's do that. This down here, I think we can lose it. And let's see if we can evaluate that integral. Okay. First one, not too bad. What's that? ln of x, absolute value x. Okay? Minus. Now what are we going to do with that next one? Can I what? I just couldn't hear what you said. No, you don't need that, because if that was a 1 on top, that's what it would be. With an x on top, what do we do? Substitution, what would be your substitution? Let u equal x squared plus 2. Then du is equal to 2x dx, right? And we only have x dx there, so we'll divide everything by 2. Okay? So now we have, that integral is now minus, we're going to pull out the 1/2, okay, the integral of du over u, okay, minus, okay, close. Because that the du winds up being a 2x, what we're going to do is split this into 2 pieces. The first piece is going to be the 2x dx over x squared plus 2 squared minus 1 dx over the integral, I didn't have to put the 1 there, x squared plus 2 squared. Okay, now what I did, I split that into 2x over the denominator minus 1 over that denominator. See?
Is that positive or minus? I mean, plus or minus? Because it's 2x plus 1, right?
Yeah, it's 2x plus 1, but there's a minus out in front of it, so that makes minus 1. Yep. Okay. Now, as you said, let's just write down what we got so far. This is log absolute value x. That doesn't change. Minus 1/2, and that would be what? Log u. Right? du over u is log u, right? Okay? But u is x squared plus 2. So that would be absolute value. Now there you don't need your parentheses. I mean, don't need absolute values. Parentheses will do because x squared plus 2 is always positive. Always. Okay? So that's okay. Now we need to do that next integral. Okay? And basically, the same u we had before we can put in here. The only difference there is if u is equal to x squared plus 2, du is just 2x dx. We don't need the half anymore, okay? Because we want that 2x dx, okay? So we're perfectly happy with that. So that's going to be, that next integral is going to be, oh, here, I was looking at the wrong place right here. That is going to be your du over u squared, which I'm going to rewrite. Sorry, I don't like to write it over u squared, so I'm going to write it like this, if it's okay. U to the minus 2 du. I think that's easier to integrate. It's the same thing, isn't it? Okay. Now, the last one, substitution is not going to help us here. Okay. What is going to help us here? I would say let's go to the back of the book and see if a table will help us any here. This is going to be boy. The the closest I can see is I don't see anything very close. Do you? I think the closest I can see is it's kind of like number 16, which is your inverse tangent, except it's squared. So let me see. Let's just make sure we've done everything right so far. Okay. We're just like we want it to be down to, yeah, they're going to do a trig substitution. That's what we're going to do. It's going to be messy, but it's doable. Okay. So let's do it. What's that?
These chapters have so many information.
Yes, it really does. So many options to choose from. Okay. So the trig substitution we'll do is, for this one, will be let x equal the square root of 2 times the tangent of theta. I believe that's it, isn't it? Okay. Then dx is equal to the square root of 2 times secant squared theta, d theta. Okay? Now, what we have to do is draw our little triangle. Mine's pretty ugly. Here's your theta. And the tangent of that angle theta is opposite over adjacent. Okay? So that would be x over root 2. Right? If you divided that x equal root 2 tangent theta, divide that by root 2, you have tangent theta is equal to x over root 2. So that's opposite over adjacent. Okay? Now, that numerator, the hypotenuse would then be what? X squared plus 2, isn't it? Because it's Pythagorean theorem. Or is it the square root of that? It's the square root of that, isn't it? That would be x squared plus 2 would be the hypotenuse squared, so the square root of that would be the hypotenuse. Okay, kind of miserable. Okay, now we can look at that and say, I don't know if that was useful or not. Okay. Let's plug in that, and we have, if you plug in x equal root 2 tangent theta, this will be x squared, then would be 2 tangent squared theta plus 2 squared, right? Got it? Well, that would be 2 times, it's actually 2 squared, so it would be 4 times tangent squared theta plus 1 is secant squared theta squared. Okay? So now our new integral is, it's going to be minus the integral. Your dx is the square root of 2 secant squared theta d theta over, and your denominator is a 4 secant fourth theta. Okay? Well, the secant squared up top goes in the secant fourth at the bottom, secant squared times. Okay? So what I'm going to do there is pull out the root 2 over 4, square root of 2 over 4, and then I'm going to write this as the integral of cosine squared, because 1 over secant squared is cosine squared. Cosine squared theta d theta. Okay? Now I'll go to the back of the book, okay, and do the trigonometric form. Number 35, cosine squared u du is 1/2 u. So this is going to be a minus root 2 over 4, and the integral of that is going to be theta over 2, right? 1/2 theta over 2, plus, now I'm not going to write it as sine 2u, I'm going to write it as 1/2 sine u cosine u, sine theta cosine theta, from my trig identity. Remember that? 2 sine theta cosine theta is sine of 2u, right? So I'm using that one, okay. Now, and then you have a plus c. We'll do the plus c at the end, yeah.
Theta over 2.
Yeah, that's theta over 2 right here. It's whatever this thing is over 2. And that's totally there, it's totally there, theta, okay. Now, we need to figure out what theta is. Okay. Phew. All right. I think I'm going to erase some of this at the bottom. We don't need this anymore. So I need more room to write. Big time. Okay. Okay. This last little step is just, it's going to take a lot, but not too much. It's not too bad. Okay. So let's write down what we've got so far. Log absolute value x minus 1/2 natural log of x squared plus 2 minus, now, what's that integral? Antiderivative of u to the minus 2. Negative u to the minus 1, right? Okay, so the negative is going to make that positive, and our u for this one was x squared plus 2 to the minus 1, or 1 over x squared plus 2, however you want to do that. Okay, that gets us everything up to where we are now. All right, now, our answer so far is a minus the square root of 2 over 4, okay, times. Now we first need to find out what theta is. Well, here we have theta. You see here that from up here, tangent theta is equal to x over 2, x over root 2, right? From there, from this line right here, right? So theta is equal to inverse tangent of x over root 2. Okay? So this will be an inverse tangent of x over root 2 over 2. That's your theta over 2, right? All right. Plus 1/2. Now what's sine theta? It's go back to our figure here. Sine theta is x over the square root of x squared plus 2, right? So that would be x over the square root of x squared plus 2. Cosine is root 2 over the square root of x squared plus 2. Okay? When you multiply those two together, the roots in the denominator, that just gives you x squared plus 2. So let me write my answer down again. Log absolute value x minus 1/2 the log of x squared plus 2, never negative, so you can leave that outside there. I'm going to write this as 1 over x squared plus 2. I don't know why, but I don't like negative exponents, I guess. Okay, minus root 2 over 4 times, let's make that root 2 over 8 times the inverse tangent of x over root 2. Okay, that's that term. And then we have a minus root 2 over 8. That's that times the 1/2. And here we have another root 2. So that makes it 2. So 2 over 8 is 1/4. Okay? Whoa! Okay, sorry if I'm skipping too many steps here. Root 2 times root 2 is 2. And you had a 2 times 4 is 8. 2 over 8 is 1/4 for that last term. And that would be x over 4 times x squared plus 2. Square root of that, plus c. Okay. I think that's my answer now. Okay? Let's write it out again. Log absolute value x minus 1/2 natural log of x squared plus 2 plus 1 over x squared plus 2 minus square root of 2 over 8 times inverse tangent of x over root 2 minus x over 4 times x squared plus 2 plus c. I think that's it. I think that's our answer. Let's see what when they combine, collect all those terms. Log absolute value x, yes. Minus 1/2 log x squared plus 2, yes. Now, they do something a little different here, but it's not far off from what we've got. They combine the 1 over x squared plus 2 with the minus x over 4 times x squared, x squared plus 2 in the denominator. So that would be a 1 minus 1/4 x over x squared plus 2. They combine these two terms, these two terms here, this term and that term, to be 1 minus x over 4. And divide that by x squared plus 2. 1 over 1 minus 1/4 x. Okay, same thing. Okay, so that term's all right. Now they do something strange here. I like square root of 2 over 8. They like to move the square root in the denominator, which is usually not where you want it, but that's the same thing. That's negative 1 over 4 root 2, which is the same as negative root 2 over 8. Inverse tangent of x over root 2 plus c. Yeah. Those are exactly the same answers, written in a little bit different form. Okay? Was that not a bear? Okay. Now, I say this too often probably. See how many different ways you can write that answer? And they're all correct. if we were doing a WebAssign or something like that, they're looking for one answer. And you might spend all day trying to get the different forms you could get and still not get this answer they're looking for. Either one of these answers is good. Okay, the one I had, the one I changed to, or the one they had in the book, they're all fine. Okay. Now, here's a conceptual insight. The examples in this section illustrate a general fact. The integral of a rational function can be expressed as a sum of rational functions, such as that's a rational function, right? Okay? Arctangents, there's an arctangent. And it's either arctangents of linear or quadratic polynomials. This one happened to be a linear polynomial. It could have been a quadratic polynomial. And logs, natural logs of linear or quadratic polynomials. There was a linear, there's a quadratic. Okay? Other types of functions like exponents, trigonometric functions and stuff do not appear. Inverse tangent does, but none of the regular trig functions do. No exponentials. You get logs, but no exponentials. Okay? So when you're doing these, expect to see those kind of answers. Rational functions, inverse trig functions, inverse tangent functions, and log functions. Okay? Now, the last little bit there says using a computer algebra system. If you have one, read that and do it. Okay? I don't have one, so there's not much benefit I see of doing it. It's only one paragraph with a couple of illustrations. So the summaries here, you want to do the preliminary questions and the exercises. Yay or nay? Let's see, by the way. Okay, let's see. Let's go back and do what we were doing before. They do a few more steps here that I skipped over. Okay? But we did do this. Okay. That last term that I split, here's how they do it exactly the same way. They split this into 2x over this plus 1 over that plus dx over that. This gave you a rational expression, 1 over this minus 1 over that. And this one gave you the thing that we ultimately had to do a trig substitutional inverse tangent. Okay. There was a triangle just like we had. Hypotenuse. So the opposite side was, yuck. Where did you go? Here we go. This is exactly the same triangle we had with our theta there. Tangent of theta is x over root 2. That meant your hypotenuse would be the square root of x squared plus 2. And this is where you got the sine then and the cosine. Okay. So that figure, those triangles are very helpful, especially in rational. And that gives you the last line. So we'll do the preliminary questions here. All right. Suppose that the integral of f of x dx is equal to log x plus the square root of x plus 1 plus c. Okay, we know that. The question is, can f be a rational function? That's the question. What do you think? My hint to you would be, go back to that last conceptual insight we just did. Okay? And let's see what it says. The examples in this section illustrates a general fact. The integral of a rational function, that would be your f, if it is a rational function, can be expressed as a sum of rational functions. That is not a rational function. It's a square root function, okay? Arctangents, we don't have any arctangents there of linear or quadratic, or logarithms. Yeah, we have a logarithm. But guess what? We don't have any radical functions. So I would say no. This cannot be, f of x cannot be a rational function. Let's see what the back of the book says. This is 7.5. Preliminary question. No. Get the menu in there. Okay. No, f cannot be a rational function because the integral of a rational function cannot contain a term with a non-integer integer exponent such as the square root of exponent. Just like we said. That was one. That was fairly quick. Number 2. Which of the following are proper rational functions? Okay? You answer me that. X over x minus 3. Is that proper or improper? Improper, because the degree of the numerator is equal to the degree of the denominator. For a proper, it has to be less than the degree of the denominator. Can't be equal to. So that's not proper. Let's do B. 4 over 9 minus x. Proper or improper? Proper. That's fine. So B is a proper. C. X squared plus 12 over x plus 2 times x plus 1 times x minus 3. X plus 2 times x plus 1 times x minus 3. Proper or improper? Proper, because the numerator degree is 2, the denominator is 3. Let's see if I can fit D in here. 4x cubed minus 7x over x minus 3 times 2x plus 5 times 9 minus x. Proper or improper? Because the denominator degree is x times x times x, that's x cubed. The numerator is x cubed. It's got to be, the numerator has to be degree less. So we had the proper ones being B and C. Okay? See what they got? Oh, they don't have the even ones there. Thank you very much. Okay. They only have odd answers. Sometimes they do them all, sometimes they only do odd. This one they're only doing odd. I'm convinced B and C are the only two. Okay, number 3. Which of the following quadratic polynomials are irreducible? Okay? X squared plus 5. Is that irreducible or not? Or reducible? Irreducible, okay? How about B is x squared minus 5? It's reducible. Now, we don't usually say we can factor that, but we really can, as x plus root 5 times x minus root 5. Remember, all it requires is no complex numbers. You can have irrational numbers. So that was reducible, the other is not. So they were asking which ones were irreducible, and that was A. Let's see what we got here. A. Square is already completed, irreducible. Say again. Oh, I see. I'm sorry, I didn't see that. Okay, let's do C. Here it is. X squared plus 4x plus 6. How would you proceed to determine whether that's reducible or irreducible? Okay, try to factor, you can't, I don't think. Can you? Okay, so what you do then is complete the square. Okay, and how you do that is x squared plus 4x blank plus 6. Same thing, right? Except what do? We want to find out what we can do. You take half of the 4, 2, square it, plus 4, but you just added 4, so over here you have to subtract 4. Right? Now this is x plus 2 squared plus 2. Okay? That is reducible. Okay? That could be reduced as x plus 2 plus root 2 times x plus 2 minus root 2. So that one is reducible. Okay? How about, Is reducible. It's not irreducible. Ooh, double negatives. Okay, D. How about x squared plus 4x plus 2? What would we do? Oh, wait. What am I saying here? No, that's a plus here. If that was a minus, yeah, that would be, yeah, this isn't. That is irreducible. Sorry. No. Irreducible. Okay, because that's a plus after that. This one, however, do the same thing. X squared plus 4x blank plus 2. Add 4, just like we did before. Subtract 4, just like we did before. Be x plus 2 squared minus 2. And now you can factor that. X plus 2 plus root 2 times x plus 2 minus root 2. That one is reducible. C is not. So we had A and C are irreducible. B can be reduced that way. D can be reduced that way. Let's see what they got. A, irreducible. B, we did that one. C, irreducible. And D, we did that one. Factors as, same thing I did. All right. Make sense? All right, that was 3. 4, the answer's not in there, but I think we can do it. Can I erase all those? Okay. Number 4. Let P over Q be a proper rational function. Okay? Where Q of X factors as a product of distinct linear factors x minus a sub I. Okay. Then the integral of P of x over Q of x dx, it says choose the right answer. A is a sum of logarithmic terms a sub I ln of x minus a sub I for some constant ai okay, or B may contain a term involving an arctangent. Okay, which of those you think is true?
Tangent, it has to be a
You're absolutely right. It would have to have an irreducible quadratic term in it. This says they're all linear factors. So therefore, A is your answer. Okay, you're right. The answer's not in the back, but I'll back you up on that one. All right, good deal. Homework exercises. Then do any of the odds, either 1 or 3, or both if you choose. Do either 5 or 7, or both if you choose. And then you get a whole bunch to pick from any of the odds 9 through 45. Okay? Now you can also do any of the odds either 47 or 49, or both, and any of the odds 51 to 57. Good deal. Any questions? No. I usually look to see if there's any potential paper topics. I don't see any there. All right. How are we doing on time? You have time? None of the three of us wear a watch. I don't know what this is. 10:15. 10:50. Okay, I was going to say, wow, this is going fast. No, 10:50, we've got another 20 minutes. Okay. Now let me see. Yeah. All right. 7.6 is a section that kind of ties up all the previous sections. So I think it's worth doing. Okay. In Chapter 5 and the preceding sections of this chapter, we've seen a variety of techniques for evaluating various integrals. However, in the real world, when confronted with a given integral, it will not appear as in a particular section devoted to a particular technique. Hence, it's important to be able to recognize which technique of integration is likely to apply. This section is devoted to that topic. In addition to considering how to recognize what technique to apply, we also discussed how tables of integrals and computer algebra systems can be used. Okay? Often an integral that comes in a particular application of calculus is a definite integral with limits of integration. In the worst case scenario, when none of the techniques yields an answer, numerical approximations can be used to find numerical estimate of the value, and that's if you have a definite. Okay. In general, there's no hard and fast rules for evaluating a given integral, but there are various heuristics, okay, that help us determine which are likely to apply. All right, so here are some of the steps you might choose. First thing you ask, oh, wait, I'm sorry. Let me get out of this and into the next section. This is section 7.6. I don't think they're going to have any of these in here, but we'll take a look and see. This is a pathetic PowerPoint that they have in this text. I'm hoping that sometime in the future, hopefully near future, we'll change text to something that's a little bit better. Okay, we'll go from the current slide. Yeah, there's nothing here. Goodness gracious. Am I in the right section? No, this is 7.7. In our book. In your book, it's 7.6. Okay, 7.6 doesn't appear in the old. The new edition 7.6 doesn't appear in the old. So basically, like I said, this is just a review of what we've already done. It's just doing. So you won't find this directly in yours. You'll find it in yours. Okay. Yeah, that's 7.7. So the title is Strategies for Integration. I don't think you have that topic, do you? Okay. Yeah, 7-7 in your book is our 7-8, which is probability and integration. And then 7-9 is numerical integration. Yeah, that's your 7-8, right? And then that's the end of the chapter. So you see, this 7-7 is not in your old book. And it just wraps up, it just summarizes what we just did. Okay? So I'll try to hit this. I was looking at it and said, I don't think there's going to be any slides. I was right. There aren't any slides because the section isn't even there. But actually what I think I'll do is rather than do that one, I'm going to do something else. My work study student did this for me. Put in just a blank slide. So that's what we're going to do now. All right. Here are some of the steps. First step, let me get my black pen back. Okay. First step. You answer this question. You do this. Do any algebraic simplification possible? Okay. For instance, factor and cancel out common factors. Okay. So here they give a few examples. A, what if your integral was x cubed minus 1 over x minus 1? What would you do? Remember back in pre-calculus when they said, can you factor the sum or difference of two perfect cubes? Yeah, you can. And that numerator will factor, and one of the factors is x minus 1. All right, so that's what you do. You factor the numerator and then cancel it out. That would be integral, and the factorization of x cubed minus 1 would be x minus 1 times x squared. How you get this is square the first term, opposite the product, square the last, over x minus 1. X minus 1 goes out, dx, and then you can integrate that. That's a piece of cake, right? Integral of x squared plus x plus 1 dx. Yeah, that's easy to do, right? What would it become? What would that integrate to? Antiderivative, right? What would it be? X cubed over 3 plus x squared over 2 plus x plus c. Got it. Okay. Good deal. Now, how about this one? The integral of x minus x cubed over the square root of x dx. That's not exactly a factorization, but there is something you can do. Okay, you could do that, but actually it's not going to be helpful. What we do is, now, here's a hint. When your numerator is a sum or a difference, or several terms, but the denominator is a monomial, we put each term over the monomial and deal with them that way. Okay? So what you would do here is rewrite this as the integral of What's x over root x? That's the square root of x. Minus, what's x cubed over square root of x? Okay, let me give you another hint. Rewrite this as x to the 1/2 power. Okay, and if you rewrite that as x to the 1/2, I would rewrite this. This would be x to the 1, which is x to the 2/2, and that would be x to the 1/2, and this 3 would be 6/2, right? And subtract that minus x to the 5/2 dx. You see that? Anytime you have a monomial in the denominator, see if you can simplify the numerator by splitting it up that way. Is it time? Oh, it's not. You have to leave early. Okay. All right. So if that is your case, and it says that can be easily integrated, do you agree? Yeah. Okay. We won't mess with it. Let's look at C. What if you have the integral of 1 over sine squared x dx? Okay? What would you do with that? I usually think of going the other way on this one. But this way actually is, most of the time if I have secant, cosecant, or cotangent, I change it back to sine, cosine. In this case, go the other way. Write that as the integral of cosecant squared x dx. And the antiderivative of cosecant squared is cotangent, or minus cotangent squared. So that would be minus cotangent squared, minus cotangent x plus c. Okay. Now, again, I'd use the back of the book. I would change it to that and then use the back of the book, because I don't remember whether it's a plus or minus. Just looking at the book, I do remember it is a minus, but rather than trust my memory, I always check it. Okay. All right, that's C. How about D? What if you, okay. I'll show you this one just because if you have this as a function, e to the x hyperbolic sine of x dx. Well, as I've told you before, I find hyperbolic signs almost confusing at best and almost useless at worst. I mean, I don't ever run into them. However, if you look up and see what a hyperbolic secant is, and by the way, that's in the front of your book, in the, not the algebra section, well, I may be wrong. I thought it was here. I don't see it. Sorry about that. Maybe it's in the back. Yes, okay. I believe it is. Elementary functions. You have power functions, inverse trig functions, exponential functions, and logarithmic functions. Then you have the hyperbolic functions. And there's your inverse, there's your hyperbolic sign right there. And rather than try to memorize anything with it, just rewrite that as the integral of e to the x, and hyperbolic sign is e to the x minus e to the minus x over 2, okay, dx, okay? So rather than trying to memorize some stuff for hyperbolics, write it back in terms of exponent, okay? And then this is a fairly easy thing to do. You get the 1/2 out front, okay? And then e to the x times e to the x is e to the 2x minus 1. Because e to the x times e to the minus x, that's e to the x over e to the x, that's 1, okay? Dx, and that's easy to integrate. This is 1/2. What would that be? E to the 2x over 2, right? Minus x. So that would be 1/4 e to the 2x minus 1/2 x plus c. Okay. They put it e to the 2x over 4. I put 1/4 in front. Minus x over 2, I put 1/2 x plus c. Okay. How we do it on time? 5 more minutes. Good. Let's do number 2 here. Okay? So first thing to do, simplify algebraically anything you can. Factor, divide out common factors, if you have a monomial in the denominator, divide it. Do whatever it takes to simplify. Okay, after that, then the next step, look for substitution. To substitute, if you can. Okay? Now, anytime you recognize an integral in the form of, and this to me isn't particularly helpful, but if it makes sense to you, I mean, it's what you do, but I don't think of it in these terms. F of g of x times g prime of x dx. If you have something that looks like that could be written that way, then a substitution is going to be really easy to do. But who looks at it and says, oh, that's what that looks like? You just look and see if it does. I mean, you don't do a substitution, okay? The key to successful substituting is that if we want to replace g of x by u, we need a g prime to exist somewhere that we can fiddle with, okay? Now, here's a few examples of that. For instance, if you had the integral of x squared sine of x cubed, okay, dx. Will substitution help you there? Absolutely. Okay, and here's where I look. This is sort of saying the same thing they are, but I like my terminology better. Look for the innermost part of the most complicated part of your problem. And if that is something that you have outside of that, the derivative of it, go for it. That's what they're saying with the g of, alpha g of g prime, that's saying the same thing, but it just makes, to me, make more sense, okay? How about this one? The integral of e to the sine x cosine x dx. Substitution help you there? Yes, because the derivative of the innermost part, the most complicated part of the function, the derivative of that is what you have left. Yes, that would work quite nicely. Okay? How about this one? The integral of e to the x times the square root of e to the x plus 1 dx. What's that? Yes, because the most complicated part of this is the square root here. The innermost part of this is that. You let u be that, and du is that. Yeah, you got it. It's done. Okay. So yeah. Let's do example 1 then. And they preface this with, sometimes a less obvious substitution does the trick, okay? So let's see what this one is. Find the integral of x cubed times the square root of 1 plus x squared dx. Okay? What might you try first? Let u equal what? 1 plus x squared. Why not? Okay? Then du is equal to 2x dx. Okay? Now, I like the x dx part, right? So let's get it down to that. Divide both sides by 2. And then you have then du over 2 is equal to x dx. Okay, but you still got an x squared that you can't do with, right? But if you go up here and you note that x squared is equal to u minus 1, isn't it? Okay, so what do you have? You have the integral of u minus 1, that's your x squared. You have 1/2 du, and you have a u to the 1/2 power, right? What I did was I split the x dx, put that together. That left me an x squared. The x squared is u minus 1. The x dx is 1/2 u du. 1/2 du. So I put that in there. And this is the x squared that was left. And this is the square root of u. Because that was what du was, right? Okay? Okay, yeah. What I did, once I did this, then I rewrote this integral as the integral of x squared times the square root of 1 plus x squared times x dx with a 1/2 out in front. Right? Well, no, let's not put the 1/2 out in front yet. Sorry. That is the same as what we got there, right? Isn't that? Those two are exactly the same. I just split an x dx from the x cubed, that left the x squared, square root of 1 plus x squared, x dx, right? And the x dx is 1/2 du. So that would be, then this becomes 1/2 the integral of, your x squared is u minus 1, your square root of 1 plus x squared is u to the 1/2, right? And then the x dx is du over 2. I put the over 2 out front. So that gives it to you, right? What do you do with that then? Say that again. Okay. What do you do with the u? Okay. Distribute. Okay. That'll be the integral of u to the 2/2 times u to the 1/2 is u to the 3/2 minus u to the 1/2 du, right? Well, I think we can integrate that, can't we? What would that integrate to? U to the 5/2 times 2/5. Divided by 5/2 is times 2/5, minus u to the 3/2 times 2/3. Okay? And then plus C. Okay? So to simplify that a little bit, that would be u to the 5/2 over 5, because the 2's canceled out there, minus u to the 3/2 over 3, because the 2's cancel there too, plus C. I hope that's what we get. Let's see if that's what we get. Oh, and then we go back and plug in what u is. U is 1 plus x squared. So this is 1 plus x squared to the 5/2 over 5 minus 1 plus x squared to the 3/2 over 3 plus C. Yeah, 1 plus x squared to the 5/2 over 5 minus 1 plus x squared plus to the 3/2 over 3 plus C. All right, out of time? Okay. We'll begin next time on example 2. Okay? And we'll go from there. All right. I will